that we are going to do is we're going to look at section 9.1, which is area between curves. So if you think way back to Calc 1, right? If you think about Calc 1 is when you first learn about the integral, right? So when you first learn about the integral from a to b of f of x dx, what that means. So going back to Calc 1, does anyone remember what that means? Right? So, means what? Okay, so yeah, it's the integral of a function, and then, yeah, so it's the integral of a function, and it represents the area under the curve f of x between a and b, right? So this represents the area under the curve f of x from a to b. So we've looked at area under a curve. Today what we're going to look at is area between two curves. So in terms of a picture, let's say here's my curve. We'll call this one f of x, and we'll call this one g of x. And let me go close my email so that we don't keep hearing the ding all the time. I usually do that before class, and I forgot. And so I know that gets annoying to hear. Okay. All right, so we're looking for the area that is between these curves, and let's suppose that this place where it crosses here, we'll call that A, and this place where it crosses here, we'll call that B. So I'm looking for the area this time that's between those two curves. So if you remember, right, so we just talked about how the integral represents the area under the curve. So for instance, the integral of f of x, just f of x all by itself, would be this whole pink area, right? So the pink area here would be representative of the integral from a to b of f of x dx. And then if I took away the part under g of x, so right? So now you have the integral from a to b of g of x dx. What should I do with those two integrals to figure out that area that I'm looking for, right? So the area that's between these two parts. So we're looking for the area in here. Yeah, so if I subtracted them, then I would get the area, right? So the area between f of x and g of x is basically going to be the difference of the two integrals. Now, we can actually do the subtraction within the integral since we're in both of them, we're evaluating from a to b. This is actually, we can simplify it a little bit and say it's the integral from a to b of f of x minus g of x dx. So some people like these problems after doing all the crazy integration stuff because they tend to be a little easier, especially just the area between curves ones. So that's what we're going to do. Doing these problems requires you to have a good understanding of what the functions look like. Okay, so you can stick the functions in a calculator to graph them if you don't know what the functions look like when you're going to do these problems. So that's not a problem. But generally, I'm going to draw a picture of all of them so that we have a good idea of what's going on. So questions before we actually do some examples? No? Okay. All right, so my first example here is find the area enclosed by y equals x to the fourth and y equals 8x. So first thing I'm going to do is I am going to draw those curves. So y equals x to the fourth, it kind of looks like a parabola, but it's a flatter bottom than our parabolas usually are. So kind of looks something roughly like that. You just need a rough picture to be able to figure out what's going on. So this is going to be y equals x to the fourth. And then 8x is just a line. So, oops, should start here. It goes through 0. So here's 8x. Y equals 8x. So we are talking about this area in here. Okay, so couple things we're going to need to do. So one is, when I do these problems, I like to think about if I was drawing in kind of like a little slice of the area, right? And so I use that little slice to help me figure out what's my top function and what's my bottom function. So in this case, what's the top function? Yeah, the 8x. So we're going to have the top area, which is 8x, minus, what's the bottom function? Yep, x to the fourth. So we're looking at integrating that difference. And then we have to figure out where we're going from what point to what point. So this one is easy, right? That's going to be 0. But we have to figure out where where we're going to end up integrating up to. So any ideas how I might go about doing that? So what's happening between those two functions at that point? The two functions are what? Yeah, so the two functions at these points here, at this point here and this point here, these two functions are exactly the same. So what we're going to do is set the two functions equal to each other. So we're going to set 8x equal to x to the fourth. To solve this, right, you can't just divide by an x. You have to move everything over to one side and factor. So we're going to have 0 equals x to the fourth minus 8x. I could factor out a 3. So 0 equals, not factor out a 3, factor out an x. X times x cubed minus 8. And then if we set each of those pieces equal to 0, we're going to get x equals 0, or x cubed minus 8 equals 0. The x cubed minus 8 equals 0, that's saying that x cubed has to be equal to positive 8. Or x is equal to the cube root of 8, and the cube root of 8 is 2. So we're going from 0, which we already knew just based on our picture, to 2. So we want to integrate this from 0 to 2. Questions? No. So now it's a fairly easy thing to integrate, right? What's the integral of 8x? Leo, yeah, that gives us the boundary. When you set the two equal to each other and you solve it, that gives you the boundaries on the limits of integration. No problem. So now we're going to integrate. So what's the integral of 8x? The derivative of 8x is 8. Remember, we're going the other way. Yeah. So remember, you go up on the power when you integrate, right? So we get 8x squared over 2, or 4x squared. You could just write 4x squared if you want. That's totally fine. Minus, what would be the integral of x to the 4th? X to the 5th over 5, evaluated from 0 to 2. So yeah, this cancels, gives us a 4. So we have 4 times 2 squared minus 2 to the 5th over 5 minus 4 times 0 squared minus 0 to the 5th over 5. So we end up with 16 minus 32 over 5. And if you do that subtraction, you would end up with 48/5. So the area between those two curves is 48/5, whatever unit, right now we just have these functions. So it's just units squared. But like if you were measuring something, if it was a real world problem, these were feet, it would be feet squared, right? Because it's area. Questions? No. Okay, so let's do another one. So how did I write these? Find the area enclosed by. Okay, I just wrote it as an example. Find the area between the given functions. This way I don't have to keep writing find the area each time. So A, y equals 1 minus cosine x times sine x. Y equals -3, and x is between 0 and pi. Okay, so in this problem we were given kind of 3 pieces to help us draw our picture. Again, being able to know what 1 minus cosine x times sine x looks like, that's not something you're going to know what the graph of it is off the top of your head. So again, you're going to want to put it into a graphing calculator, put it into Desmos. Desmos is an online graphing calculator, right? So Desmos, that works really well. Any of those is totally fine, so you get a good picture of what's going on here. So the function 1 minus the cosine, or 1 minus cosine x times sine x looks roughly something like that. And it does some other stuff. This point here actually happens to be pi. Or actually, no, it doesn't. I read my graph wrong. Let me redraw this a little bit better. So it's kind of looking like that. Okay, so this is that y. We have the graph y equals -3. So y equals -3 is a straight line this way. And then x's are going between 0 and pi. So it's not important to really know exactly where pi is here. So basically, we're looking for maybe pi is someplace here. So again, I don't have like a perfect graph drawn. I just have like a rough graph drawn. And so in this case, we're looking for this area under these curves. So again, When you go to find the area under the curve, you want to think about if I put in a slice. That's kind of the most important thing here. So I'm sticking in a slice. So where is the top of that slice? You guys are very quiet today. Okay, I got that blue line. The top of that blue line. It's on which curve?
The 1 minus cosine?
Yeah, the 1 minus cosine x times sine x, right? So we have 1 minus cosine x times sine x, right? This is what I think of as the top curve minus the bottom curve. And what's my bottom curve in this case? Yeah, -3, so minus -3 dx. And then in this case, they even just told me where x is between. X is between 0 and pi. So I know exactly where I have to integrate these between 0 and pi. Right? I should have been a little careful because where I just drew that 0 and pi, that's not the axis, right? Here's 0, and then there's my pi already. Okay, so this becomes the integral from 0 to pi of 1 minus cosine x sine x plus 3 dx. Now we're going to have to do a little bit of work to integrate the 1 minus cosine x sine x part. So I'm going to split it into two integrals here. So integral 0 to pi, 1 minus cosine x sine x dx plus the integral 0 to pi of 3 dx. So 3 is going to be easy to do. What am I going to have to do to integrate 1 minus cosine x times sine x? Yeah, use substitution. You might have been thinking integration by parts. I'm going to say you probably maybe could get it to work with integration by parts, but it's going to be a lot of work and messy. So in this case, if you did a u substitution, if you let u be the stuff inside the parentheses, the 1 minus cosine x du would turn out to be, so the derivative of cosine is negative sine, but you have that negative already. So du is going to be just sine x dx. So this is going to become the integral from, I'm going to write x equals 0 to x equals pi, so I remind myself those are x limits, of u du. So we're just going to finish this first integral first here. So the integral of u is u squared over 2. So we get u squared over 2. And then in our case, u is 1 minus cosine x. So 1 minus cosine x over 2. Excuse me. What's the integral of 3? So let's take care of that one now. (3x), yep, so this part is going to come, so plus 3x, and we're evaluating both of these parts between 0 and pi. So now all I have to do is plug in pi, so we get 1 minus the cosine of pi over 2 plus 3 pi.
Is there meant to be a square on the 1 minus?
Oh, yeah, there is. Thank you. Yes, thank you so much. I see Aiden asked too, and I didn't even see over there. Yeah, thank you guys for catching that. So I have 1 minus cosine of pi squared over 2 plus 3 pi minus 1 minus the cosine of 0 squared over 2 plus 3 times 0. So remember the cosine of 0 is 1. So this part here is going to be 1 minus 1. So this part's going to go to 0. This goes to 0. So I don't have to worry about that. The cosine of pi is negative 1. So we're going to have 1 minus negative 1 squared over 2 plus 3 pi. Or 1 minus negative 1 is 2, so 2 squared over 2 plus 3 pi. So 4 over 2, which is just 2 plus 3 pi, is our final answer. Questions? Yeah, so the cosine of 0, yeah, so I have that here, right? So the cosine, it's kind of underneath here. The cosine of 0 is 1, but then you have 1 minus 1. So 1 minus 1 is 0, so the whole thing goes to 0. Sure. No problem. Move it back down here. Other questions on this one? No. Okay, so let's try another one. So B, we have the curve x equals y squared plus 1, and the curve x equals 2 minus 3y squared. So these curves are a little different because they're not solved for y, right? They're solved for x. So remember, when stuff is solved for x, it's kind of like you took, everything's kind of drawn sideways, right? So it's kind of like if I drew the curve x squared plus 1, but then knocked it like 90 degrees. That's essentially what's happening here. So again, you can graph these on Desmos. You could also do a rough sketch if you flip-flopped them and called it y equals x squared plus 1 and y equals 2 minus 3 x squared. That would give you a good enough sketch to figure out like what is the top curve and what is the bottom curve. So the curve x equals y squared plus 1, though, goes through here at 1, and it's a parabola. It's just opening sideways. So this is the curve x equals y squared plus 1, right? So I can pick up my iPad here, right? So, but if you think about it, like, let's see, I could probably do this. So like that's, well, of course it's going to flip on me. So but you can think about it. If I turned it, right, that would be the, like, regular, what we think of x squared plus 1, and then you're going to flip it onto its side. So that's kind of, thought it'd be all cool, and then it didn't work on me anyway. X equals 2 minus 3y squared is going to be a parabola that opens down, right? So it's going to look something like this. So 2 minus 3y squared. And when y is 0, x would be 2. So it's actually here at 2. Okay, so when your curves are sideways, when they're solved for x, we have to think about, rather than drawing that up and down little blue rectangle, little blue line, we want to think about going sideways. If I drew it up and down, I'd kind of run into a problem, right? So let me show you. Here, I'll do it in pink, but then I'm going to erase it. So if I drew this up and down, I run into a problem because the top of my little rectangle and the bottom of my rectangle are on the same curve. And so it's like, well, there's not two separate functions. So you want your little rectangle to be in there in a way where one side is on one function and one side's on the other function. And again, because everything is kind of knocked on its side, the thing you want to remember is that this here is the top and this part here is the bottom. So our integral is going to be the top function, which is the 2 minus 3y squared, minus the bottom function, which is the y squared plus 1. So I have the top function minus the bottom function. And then this time we're going to integrate with respect to y, so dy, because basically, essentially what we're doing is we are finding the area of a little tiny rectangle. So this little tiny rectangle, if you think about the area of a rectangle, it's base times height. So the height is being represented by this difference. This is the height. And the base is just a tiny little sliver. So we think of the base as a dy or a dx. So this is the height times the base, right? Or length times width, so you can think of it. And so the only thing we have left to do here is we have to figure out our limits of integration. So how am I going to figure out my limits of integration?
Setting the two functions equal?
Yeah, setting the two things equal to each other. So we're going to take 2 minus 3y squared. We're going to set it equal to y squared plus 1. So if I bring all the y squared, say, over to the right-hand side, I'd have 4y squared plus 1 equals 2. Subtract 1 from both sides. So 1 is equal to 4y squared. Divide everything by 4. Y squared equals 1/4. So y is going to be equal to, we're going to take the square root of everything. So it's going to be plus or minus the square root of 1/4, or y is going to be plus or minus 1/2. So we're going from minus 1/2 to positive 1/2. And so really we want to integrate 2 minus 3y squared minus y squared minus 1 from minus 1/2 to 1/2 dy. You don't have to put the things together. I'm going to put them together to make my life a little easier so I don't have to integrate as many pieces. So we're going to have the integral from minus 1/2 to 1/2. 2 minus 1 is just going to be 1, and then a minus 3y squared and a minus y squared is going to be minus 4y squared dy. And then the integral of 1 is going to be what? Y, right? And the integral of 4y squared is going to be? Yep, 4y cubed over 3. Minus 4y cubed over 3. And then we're going to evaluate that from minus 1/2 to 1/2. So we're going to get 1/2 minus 4 times 1/2 cubed over 3 minus 1/2 minus 4 times minus 1/2 cubed over 3. So we've got 1/2. 1/2 cubed is 1/8. So this is going to be minus 4/3 times 1/8. Minus 1/2 will give me plus 1/2. Minus, it gives me again plus 4/3 times minus 1/8. So I've got 1/2 and a 1/2, that's 1. Then I've got minus 4 over 24, right? Minus 4 over 24. So I've got 1 minus 8 over 24, or 1 minus 8 goes into 8 one time, 8 goes into 24 three times, so 1 minus 1/3, which is 2/3. Questions? not terrible problems if you can figure out how to kind of draw that rectangle. So, okay, at the very beginning, you could have solved for y, yes. The problem is if you solve for y, you're going to have plus or minus each half. So you're going to have, because you have to take a square root, because the y's are squared. And so then you're going to have to break your problem into multiple pieces, because you're going to have 2 parts of y for each of those ones. So it's actually a way easier problem if you don't solve it for y. It's not that you can't do it, it's just, but it is easier if you don't do that. Other questions? No problem. Okay, should we try another one? Okay, so find the area, in the first quadrant, bounded by y equals e to the minus x over 2. Y equals e to the x equals 0, and x equals 2 natural log 2. So again, I'm going to draw a picture. So my first curve, y equals e to the x, looks like this, right? And e to the x crosses through at 1. Y equals e to the minus x over 2 is going to come down in the other direction. So you have a curve that's coming down like this. So this is y equals e to the minus x over 2. X equals 0 is this straight up and down line here, right, on the axis. And then x equals 2 natural log 2, you know, maybe that's someplace here. So 2 ln 2. So we're talking about this kind of triangular shaped region in the middle there. Right, that's the region that's bounded by all of those functions. Any of the other regions you would pick would be missing one of those functions. Questions? Okay, so again, we're going to stick in a rectangle. So since our functions were solved for y equals, like, we're going to think about putting our rectangle in straight up and down here. So what is our top function there? Okay, y equals e to the x, so we're going to have e to the x minus, what's my bottom function? E to the minus x over 2 dx. And then in this case, I happen to know the limits of integration already, right? On the left-hand side, I'm at 0. And I'm going all the way to 2 ln 2. And so now we just need to integrate these things. So the integral of e to the x is e to the x. Okay, and then remember, I gave you guys that shortcut that the integral of e to the ax dx is 1 over a e to the ax. So remember, minus x over 2, this is really the same as saying minus 1/2 of x. So when I integrate this, we're going to have minus e to the same thing, so e to the minus x over 2, divided by, in this case, my a is a negative 1/2. So divided by negative 1/2, evaluated from 0 to 2 ln 2. So really we have e to the x plus 2 e to the minus x over 2, evaluated from 0 to 2 ln 2. Excuse me. And so now we just have to plug in the top limit. So we're going to have e to the 2 ln 2 plus 2e to the minus 2 ln 2 all over 2 minus e to the 0 plus 2e to the minus 0 over 2. So if you have e and then 2 and ln within a number, the e and the ln would cancel each other out. So remember that numbers in front of the natural log can be pulled up as powers. So this is really e to the natural log of 2 squared. Here the 2's would cancel, but I could pull that negative up. So plus 2e ln of 2 to the negative 1. Minus e to the 0 is going to be 1. So 1 plus 2 times 1. Because I have another e to the 0. So this is going to be 2 squared plus 2 times 2 to the negative 1 minus this inside the parentheses here, we're going to have 3. So I have 4 plus 2 times 1/2 minus 3. So we really have 4 plus 1 minus 3, or 2. Questions? No. All right. You guys are very questionless today. You guys are, it's very odd. Right? I know we don't have a ton of people here. We have like 19 people here. So I know some people might decide, oh, it's the day after a test, but it's sad for them, right? Because they're missing this riveting lecture that I'm giving here today. All right. So my last one, the problem's a little bit different. So it asks for find the total area between y equals 4 minus x squared, y equals minus x plus 2, x equals negative 1, and x equals 3. So the thing that's different in this problem is that it asks for the total area. It didn't ask for just the area between the two curves. So if you remember back from Calc 1, if an area dips below the y-axis, then it's negative. Whereas here, like, so if you think back to Calc 1, when it flipped negative and we had to find the total area, we had to kind of change things. So sometimes when you have the area between two curves, right, the curves change positions. And so for a while, one curve's on the top, and then it changes, and that curve ends up on the bottom. And so that's what happens in this problem that I have here. So if we draw the first curve, and I'll do them in colors this time. Maybe this will help us out a little bit. So I'm going to draw the curve 4 minus x squared in blue. So give us some tick marks here. Okay, so 4 minus x squared opens down, and it looks like that. So it's picked up 4. It would cross the x-axis at -2 and +2. The line y equals minus x squared, do that one here in pink, or y equals minus x plus 2, crosses here at 2, and it has a slope of 1. So it's also going to cross through this point here. And then we want to go between -1, so x equals -1 is here, and x equals 3, which is here. Now, my picture is kind of bad, because I'm kind of just drawing it by hand here. But, oops. This blue line I didn't draw the best. It kind of goes more like that. So it will eventually cross that green line. Okay. So we're talking about basically this area here, and then also this area here. And so if you look, there's those two areas, and between those two areas, what is the top function and what is the bottom function changes. So this here, actually, this in here, this is area 1, and this part in here is area 2. So our total area is going to be area 1 plus area 2. So let's focus on area 1. So in area 1, which function is on top? Yeah, the 4 minus x squared. So the top function is 4 minus x squared, minus the bottom function is minus x plus 2 dx. And we're taking that from -1 all the way to this point here, which is 2, right? Now, if you didn't know that that was 2, you could easily set the two functions equal to each other, right? You could take 4 minus x squared is equal to minus x plus 2. So 0 is going to be equal to x squared minus x. 4, you're going to have 2 minus -4, so -2. And then that would factor into x minus 2x plus 1. So that's going to, if I set them equal to each other, x minus 2 equals 0 would give me x equals 2. X plus 1 equals 0 would give me x equals minus 1. So my drawing was accurate enough that I could see, oh, it passes through at 2. But if it didn't, you could just solve those two equations equal to each other to find where it is. So I've got my first part. Plus, now I have to do the area of the second one, which we're going to go from 2, and we're going to stop at 3. And now the functions are flip-flopped. So the minus x plus 2 is on top. Minus on the bottom, now I have the 4 minus x squared dx. So if we kind of clean up these integrals a little bit, I'm going to integral from -1 to 2. We're going to have 4 minus x squared plus x minus 2 dx plus the integral from 2 to 3 of minus x plus 2 minus 4 plus x squared dx, or the integral from minus 1 to 2 of, so if I write it minus x squared plus x plus 2 dx plus the integral from 2 to 3 of x squared, then we're going to have minus x minus 2 dx. It makes sense the two would be opposite of each other because we're flip-flopping the order of them. So now we just have to integrate each of these. So the integral of minus x squared is going to be minus x cubed over 3, plus the integral of x is going to be x squared over 2, plus 2x, evaluated from minus 1 to 2, plus x cubed over 3, minus x squared over 2, minus 2x, evaluated from 2 to 3. And then I just have to plug in. So minus 2 cubed over 3 plus 2 squared over 2 plus 2 times 2 minus negative 1 cubed over 3 plus negative 1 squared over 2 plus 2 times negative 1. That's all the first part. Plus the second part would be 3 cubed over 3 minus 3 squared over 2 minus 2 times 3 minus 2 cubed over 3 minus 2 squared over 2 minus 2 times 2. And if you work that all out, you should get 19 thirds. I'm just going to tell you what the answer is. So you could punch it in a calculator or figure out all those fractions and what everything is, but you should end up with 19 over 3. Questions? No? No questions? Yeah, so A2 is just A1 flipped over. Yep. Okay, go for it. Why did we have to set them equal? Okay, so you didn't have to, so kind of two parts to this answer. You didn't have to set them equal to find the beginning and the end bound. What you had to find, though, was this middle point where they crossed. So in my picture, it was obvious that this middle point where they crossed was at 2. But if that wasn't obvious to you in your picture, like if you drew a rougher sketch and weren't really sure exactly where that happens, sure, you would have to set them equal to be able to find where this was, right? So I could look at it and say this was 2, or you would have had to set them equal to each other to get it to show that it's 2. I had to find this middle spot because this is where it flip-flops, right? Before, to the left of this middle spot, the parabola is on top and the line is on bottom. But to the right of the middle spot, the line is on top and the parabola is on the bottom. Does that make sense? So I didn't need to set them equal to find the beginning and the end. I needed it to find that middle point. Other questions? Okay. So, is everyone okay if I go on to the next page? Yes? No one's telling me I can't. Okay, that is the end of section 9.1. So what we're going to do from here is we're going to transition from just doing flat, two-dimensional area between curves to actually be beginning to find volumes of solids. So this is where I'm kind of sad we're not in person, and that I don't really have access to my office, and I didn't think about this till yesterday, and it was too little time for me to get access to my office to go get some of my props for the next section. But so I'm going to draw the picture, and the pictures are fine. And I'm going to tell you about my props, which will hopefully help you out a little bit. So this is section 9.3, which is volumes by slicing and rotating around an axis. Okay, so do you guys know those decorations for a party where it's like a flat shape, but then when you open it up, it's like that whole honeycomb, and you can like twist it around, and so it's this flat shape that when you rotate it around, all of a sudden now pops into a 3D shape. Do you know what I'm talking about? Okay, so at least one person knows what I'm talking about. Yeah, okay, so you got these flat shapes, and you rotate them around to make a three-dimensional shape. That's what we're going to do here. We're going to start with a flat mathematical, two-dimensional mathematical area. And if we take that area and we rotate it around, we're going to end up with a three-dimensional shape, right? So we're going to start by taking a shape. And rotate it around. Yeah, it's kind of like a pop-up book. Wait a minute. I should have done this before, but let me see if I can Google one real quick. Let me see if this shows what I want. Maybe. Okay, so here, let me share the screen with you guys. Okay. So I'm talking about these things, right? So they're like a ball, or there's other ones, you know, you can see here, this one's a beehive, right? And if you've ever put them together at a party, right, what happens is they look like this to begin with, right? So this one here is going to turn into a bell, because, so it, you know, that's the little bottom part of the bell, and if you rotate it around, then it turns into the three-dimensional shape, right? So there's a bunch of different type ones. Does that make sense? Right? You take, in this one, you can kind of see how they took the shape and then they rotated it around, and then you've seen, and then you have that like three-dimensional shape, right? And so I have things like these in my office, which I then bring to class. but I don't have any here at my house, unfortunately. I have puffball type things, but I don't have these guys. But the idea is, but can you kind of see how like it starts with like it's easy to see in kind of like something like this, right? Where that's where it was, if it had been flat before, right? You take it and it like rotates it around and it becomes a three-dimensional shape. And they make, obviously, you can see all sorts of things, apples and jellyfish and, you know, all sorts of different things, cactus and stuff like that, right? So that's the idea of what we're going to do. We're going to start with a flat shape and we're going to rotate it around and it's going to pop into this three-dimensional shape. Okay, let me stop sharing that. Let me go back to sharing my iPad. Recording it. Okay, so we are going to start with that flat shape and then we're going to rotate it around. So, for example, right, and I'm going to draw this kind of big here so we can kind of see what's happening. Let's say that I had a curve and my curve kind of looked like this. And let's say that this was A and this here was B, right? So I have this area here. And what I'm going to do is I'm going to rotate that area around. So maybe I'm rotating it around here, the x-axis, to create a three-dimensional shape, right? Now, when I draw it, I just kind of make a mirror image of this shape. And you're talking about you have this three-dimensional shape, right? So it kind of looks like a vase or something, sort of knocked on its side, right? Oops, I lost the chat. What happened to my chat? Yeah, see? You read my mind before I even said it. It's a vase. Okay, so I have this three-dimensional shape. So we're going to come back to this shape here in a second. So you guys have probably, I'm assuming that most people have been to, in the grocery store, like a deli counter, right? Where they take the giant block of cheese or they take the giant thing of meat and they stick it on the slicer and they like start slicing, you know, pushing and slicing the pieces off, right? Yes, no, you know, kind of what I'm talking about. Okay. So, if I took like a big block, so say I took a big block of provolone cheese. Yeah, it really kind of is the only way to go for sandwiches. So say you take a big block of provolone cheese, right? So it's round, so it's a cylinder, and I put it on that deli slicer and I start slicing it and I start making all of these really thin slices of cheese. If I wanted to, after I had all those really thin slices of cheese, I could lay them and stack them back up to remake the block of cheese, right? So you're slicing it into these slices, but the volume is made by taking these slices and stacking them up. So that's how we're going to find the volume of these things. We're going to think about, we're taking slices of this shape, right? So maybe here's my slice, and my slice has just a tiny, the ever tiniest bit of width. And we're going to want to find the area of that slice, right? So we're going to find the volume. So the general idea is we're going to find volume by taking discs and adding up the area of all the discs. Yeah, so exactly. So like a Riemann sum. So when we did Riemann sums before, a Riemann sum added up an infinite number of things. And remember, a Riemann sum turned into a what? So we did Riemann sums to be able to find something. Yeah, so Riemann sums turned into an integral, so we're going to use an integral to help us add up all these slices. So let's just first talk about the area of a disc. So the area of a circle, right? I know mine look a little oval in here, but they're really not. They're really circles. That's just the perspective of the drawing. So how do you find the area of a circle? Okay, it's pi times r squared, right? So the area of a circle is pi r squared. So our radius starts here, and our radius goes up, and it happens to live on the function. Now the radius changes as we move left or right on my shape here, but that radius is still always on the edge of the function. So the r is really just the f of x, whatever your function is, squared. So the area of that disc that I drew in there, that representative disc, is pi times r squared, but in this case it's pi times f of x squared. Oh, that's cute, Aiden. I like it. We are going a little bit in circles. So, and then I want to add up all these areas. So the volume, to get the volume, so the volume is going to be the integral from a to b of pi times, I'm just going to write the radius. And the reason I'm going to write that is because depending on what your radius is, right, it's going to look a little different. So pi times the radius squared. And in this case, it's going to be dx. So a little note about this here. We could do dx or dy. If your slices are going in like this way, we're going to be doing dx. If your slices are going in this way, which I have some examples, we're going to be doing dy. So think about it. If dx is the vertical, and the reason why is because this little part, the width of the slice is slicing through the x-axis here. The width on a dy would be slicing through the y-axis. So that's the general thing we're going to do. We're going to draw a picture. We're going to think about what it looks like when I rotate it around, and then we're going to think about finding these discs and adding them up. Questions on the general idea? No. Okay, then let's try some examples. Find the volume.
Dr. Gorman?
Sure.
Could you go back to the last slide for just
Sure.
30 seconds?
Yeah. It could be for longer than 30 seconds, not a problem.
Okay, thank you so much.
No problem. Anybody else need me to wait? No. Okay. So, find the volume of the solid formed by revolving the region bounded by the graphs y equals the square root of the sine x and y equals 0 from 0 to pi about the x-axis. So I'll give you guys a minute to kind of copy that down here. So, just like in my area problems, I want to first draw the region. I'm going to do the same thing here. So, if you stick into a calculator, y equals sine x, or square root of sine x, you'll see that you end up with this piece here, which actually goes from 0 to pi. And when I draw these, I generally tend to shade in my original shape. Different people do different things. So like, for instance, Professor King, he never draws the three-dimensional picture because he's like, I'm not good at drawing and I just don't do it. He just draws this part. And then rather than put in a disc, he still puts in the rectangle like you do with the area and uses that. I personally, like, I don't mind drawing, and so I like to draw the three-dimensional shape, but you don't need to. But if I am going to draw the three-dimensional shape, I always want to shade in what my original shape is, because that's what I'm going to be using as my, like reference point. Yeah, it is. I do actually like to do it because I do really like art. I mean, I got a PhD in mathematics, so obviously I like mathematics. But I've always done artistic things on the side, and so part of that is, that's probably why I like to draw this stuff. So the easiest way to draw these shapes, though, if you want to draw a three-dimensional one, is to actually just do the mirror image of what you see over where you're rotating. So we're rotating about the x-axis, so I'm just going to draw the mirror image here on below the x-axis. And then I just put in some circles for my discs, right? So, basically you kind of are getting like a football shape, right? I like to put my main disc in another color just so it's kind of clear here. And if you think about it, here's that radius of that disc. So it's really only the radius that Professor King would draw into the picture. Okay, and so remember the formula I said was the volume was the integral from a to b of pi times the radius squared, d something. So when I do these problems, the first thing I do is I figure out, am I dealing with dx or dy? So in this case, because that disk is straight up and down, it's a dx. So my volume is going to be something, I generally pull the pi out in front of the integral because the pi is just a constant. It's just a number. So rather than muddy up inside my integral, I like to keep it out in front. So we have pi and integral. So I'm going to have some radius squared. So something squared. And then in this case, we're dealing with dx. And then the next thing I do is I figure out what's squared. So my radius here is sitting on this curve, right? So that's what the radius is. The radius is just going to be that curve. So it's going to be the square root of the sine x all squared. And then in this case, I'm stacking up those discs, starting at 0 and going all the way to pi. Questions about anything I did so far? So I honestly think that the hardest part in these problems is setting up the integral for the area or for the volume, not necessarily in doing the actual integration. The actual integration usually isn't too terribly bad. But it's the setup part that's hard. And the nice thing about this problem is you have a square root and a square, so those would undo each other. So this is just going to be pi, the integral from 0 to pi of sine x dx. And the integral of sine x is what? Yeah, minus cosine x. So we have pi times minus cosine x evaluated from 0 to pi. So we have pi times minus cosine pi minus cosine of 0. So we've got pi times minus Cosine of pi is minus 1. Minus minus is a plus. Cosine of 0 is 1. So I really have pi times 1 plus 1, or 2 pi. So the area, or not the area, the volume is 2 pi. Questions? It's not too bad, right? The other kind of little giveaway is if you're rotating around the x-axis, you're going to be doing dx. If you're rotating around the y-axis, you're going to be doing dy. I should be a little careful when I say that. It's for these things called disks. That's what we're doing right now, is called the disk method. Next class, so on Tuesday, we're going to do 2 other methods. So one is called the washer method, and so that still holds in the washer method. If you're revolving around the x-axis, you're doing dx. If you're revolving around the y-axis, you're doing dy. And then there's also the shell method, and so the shell method it doesn't hold us. That doesn't hold. So you want to be a little careful. It's not all the time. It kind of depends on the method you're using. But for right now, for what we're doing so far, if we're rotating around the x, you're going to go dx. If we're rotating around the y, you're going to go dy. Does anybody need me to wait before I move on to another page? No? Okay. So let's try another one here. So find the volume created by rotating the area bounded by the x-axis, the y-axis, and y equals the square root of 9 minus x squared about the y-axis. I should have left myself a little bit. Okay, so the x and the y-axis, those are the straight up and down ones, right? The other part we have is the y equals square root of 9 minus x squared. So y equals square root of 9 minus x squared is actually the upper half of a circle of radius 3. So you have radius, and you basically have that. But then we're also bounding it by the x-axis, so the straight up and down part, and this part here. So you can think of it as, you could have taken either side. So that's kind of like our original area, and we're going to rotate it around. So I've already drawn its mirror image on the left-hand side here. And so if we're rotating it around, it looks like that. So it's kind of like a dome. And if you think about putting in a shell, not a shell, a disc, right? Here's my disc. And here's that radius of my disc. And you can't really see it anymore Remember, this goes up here to 3 because really, like I said, this y equals square root of 9 minus x squared is a circle of radius 3, right? Because you can think of it as I had y equals square root of 9 minus x squared. That's really saying you have y squared equals 9 minus x squared, or x squared plus y squared equals 9. So that's kind of how I knew that it's the upper part. The plus square root gives you the upper part of the circle. The minus square root gives you the bottom part of the circle. Okay, so my volume is going to be pi something squared d something. So in this case, I rotated around the y-axis and my discs are in sideways. So because my discs are in sideways, I'm going to be dealing with dy. Now, as soon as I see dy, that means what I put in here for the radius must be in terms of y. My radius right now is in terms of x, right? So I cannot take this square root and just plug it in here, because all of a sudden I'm going to have x's in this part, but dy, and that's an issue. So if I have a dy out here, I need to have y stuff in here. Now, sometimes you might have been given the function already solved for y. Sometimes you might not be. So in our case, we weren't. So we have to solve it so that it's a function in terms of y. And I'm already kind of halfway there, right? Because I squared stuff down here. So if I keep working with this and I solve this for x, this is going to say x squared is equal to 9 minus y squared. So x is going to be plus or minus the square root of 9 minus y squared. And again, because we're above, we're talking about that positive part, this is going to be the square root of 9 minus y squared. Now, some people might go, well, so I could just swap the x and the y all the time? No, you got lucky in this problem, you can do that. But depending on the problem, you might not be able to just flip-flop x and y. So just be a little careful, actually work it out to solve it for x. And then I'm adding up those slices. I'm starting here at the bottom, down here, and so that is actually at y equals 0, and I'm adding them up to this point up here, which is y equals 3. Questions? No. Okay, so this is, again, not too bad of an integral to do. I have pi times the integral from 0 to 3 of 9 minus y squared. That's a terrible looking 0. dy. So pi times 9y minus y cubed over 3, evaluated from 0 to 3. So we get pi times 9 times 3 minus 3 cubed over 3 minus 9 times 0 minus 0 cubed over 3. So we're going to have pi times 27. 3 cubed is 27, but 27 divided by 3 is 9. So 27 minus 9, right? This whole second part here, this all just goes to 0. So 27 minus 9 is 18. So we end up with 18 pi. Questions? No. Can I go to the next page? Yes. Okay. So I have one more example that we're going to do today. So it's my last disc example. And then, as I said, next class we're going to do washers. So washers are used essentially, if you think about these solids that we're forming right now, they're solid. Like they're solid. I know I use the solids we're making, but these volumes we're making are solid. And so next class we're going to talk about, well, what could you do if it wasn't solid? Like, how could you figure out maybe like a bowl type shape where, like, you know, you have an outside part, but then the inside part is maybe hollowed out some. How could you figure those? Or what could you do if there happened to be a hole in your shape? So that's where we're going to use this thing called the washer method to help us out with those. All right, so my last example here is find the volume of the solid formed by revolving the region bounded by f of x equals 2 minus x squared and g of x equals 1 about the line y equals 1. Yes, so actually you can find the volume of a donut. That's a very good point, Robert. And that's actually, like, I don't know if you guys remember, but there is on our, like, syllabus, right, there were things called projects, right? So I'll usually ask area between curves on a test, but I don't usually ask the volume problems on the test, just because they're a little long or they're a little contrived sometimes. But after I finish volumes, I actually usually, when we're in the classroom, so I can't do this now, but I usually actually bring everybody, I bring in donuts, and I give everyone a donut, and then when you're all enjoying your nice donuts, then I say, hi, your project is actually to use math to find the volume of a donut. So there is a project coming that has you actually work through finding the volume of a donut, and it steps you through the steps. So, but yes, so it actually is coming, and that was a great segue. So thank you for doing that for me. I know, you did. You missed out on donuts because of COVID. I'm sorry. So, yeah, you missed out on a bunch of things. You missed out on donuts. Sometimes when I'm doing the volume sections, I bring in bundt cakes and start slicing them apart to show, like, stuff that's happening. I can't remember. I don't know if Brian's on here today or not, but I can't remember if in his class I brought in the bundt cakes. I might have. I might not have. I did it one time, and then when I went to do it the next year, my bundt cakes just, like, crumbled, and it was a huge mess, and so then I was...
We didn't get cake. I remember that.
Yeah.
Yeah, I think we had donuts. That sounds familiar.
Yeah, donuts usually sound familiar, so... Yeah, so I've done all sorts of different things. All right. So should we try this last one here? So we're looking at this volume. So f of x equals 2 minus x squared. That's a parabola that opens down, right? And it's up here at 2. And the function g equals 1 is just a horizontal line. So we're talking about taking this area here. So the area that's bounded between these two curves. And then this time, we're not rotating it about the x-axis. We're actually rotating it about this line here. So we're rotating it about the line y equals 1. So the mirror image would come down here. And again, it's another one of these football shapes. They're kind of boring until you begin putting holes and stuff like that in them, right? So, We'll get more interesting shapes next class. And so again, this pink part here is my radius. Okay, so my volume is going to be pi. The integral, we'll figure out the limits in a couple minutes here. Some radius squared. And then d, so again, here's where I'm not rotating around the x or the y-axis. But if you think about it, my discs are standing straight up and down here. So they're perpendicular to the x-axis. So they're going to be a dx. You can think about it, the line y equals 1 is horizontal, just like the line y equals x. Not y equals x, y equals 0, so the x-axis. So it's going to be that similar type thing, dx. The thing that's a little tricky here is most people are like, okay, cool. So I just need to plug in the function 2 minus x squared, right? That's my radius. The thing is that 2 minus x squared, the thing you want to remember is we've like taken this and we've like pushed it up. We're no longer going all the way down to the x-axis. So when you go all the way down to the x-axis, then your radius is just the function. But our radius, but the area from the curve all the way down to the x-axis is this whole part down here, and that is too much area for our radius, right? So this blue part here that I just did, this blue part, that is 2 minus x squared. That's how long that is. But that's blue is too long for my radius. So if you notice, to get the radius, I've basically taken off this green part here. And so how big is that green part? How high is that green part? Yeah, 1. So my radius in this case happens to be the function 2 minus x squared, but then I'm taking off 1. And the reason, again, is 2 minus x squared gives me this whole entire blue line. I'm only looking for this pink part. So if I take the blue part and then I take away, I subtract off this green part here, that leaves me with the radius. Questions about that? Because it's weird. As soon as you don't rotate around the x or the y axis, you have to start playing around with the radius. You can't just take the same radius. That's the function anymore. So you're usually going to have to either add or subtract something to the radius. Questions? You're still taking the integral of the entire two-dimensional shape, but only the part that's shaded, right? So if you think about it down here, there's still more of this function. There's still more area under this function that I didn't shade, that we're not using. So it's more like we're not taking the integral of the entire two-dimensional shape, not three-dimensional shape. Does that make sense? Other questions? No. Okay, so we have to we want to integrate it. We need to go from this point here to this point here. I don't know what those points are. So to find it, I'm going to have to set my two equations equal to each other. So we had 2 minus x squared has to be equal to 1. Or minus x squared has to be equal to minus 1, or x squared equals positive 1, which if I take the square root of both sides, x is going to, plus or minus here, is going to be plus or minus 1. So we're integrating from minus 1 to 1. You could, sometimes people like to do this better, if you have a shape that is symmetric, right? If you think about this is my football shape, I could just figure out the volume of half of the football and then multiply it times 2 if I wanted to, right? So there's nothing that says that you can't do that. So you're allowed to use some symmetry to help you out if you would like. So now there's nothing left to do except to integrate this stuff. So I've got pi, we've got from -1 to 1. If I simplify the stuff inside there, this is the same as 1 minus x squared, all squared dx. There's no real way around this. You have to actually just square that 1 minus x squared out. So we're going to have pi times the integral from -1 to 1 of 1 minus 2x squared plus x to the 4th dx. So we've got pi times x minus 2x cubed over 3 plus x to the 5th over 5 evaluated, between -1 and 1. So pi times 1 minus, when I plug in, I have 2 times 1 cubed over 3 plus 1 to the 5th over 5 minus -1 minus 2 times -1 cubed over 3 plus -1 to the 5th over 5. So we've got pi times what? 1 minus 2/3 plus 1/5 minus is another plus 1. Minus times minus is plus, but then -1 cubed is also negative, so minus 2/3. And then minus is a plus again, so plus 1/5. And if you work this all out, you should get 16 pi over 15, right? If you kind of add all those things together, make them all 15s. Questions? No. I put up homework for section 9.1. So the homework for section 9.1, the area between the curves, that's the homework that's due on Monday. I did put up the homework for section 9.3, but we're only like halfway through 9.3, so you can't do all the problems yet. So just to kind of let you know. And I know we technically have 12 minutes left in class, but 12 minutes is not enough time to do a washer problem or to introduce washers and do a problem. So why don't we stop there for today? But if anybody has any other questions, I'm happy to answer them.